Let's move on to recursion. So we can define a function using recursive definition. So here is the function f. This one show all the natural number from 0 to the infinity. The first step, the f0 will be 0. Next step, we can define using n plus 1 and n plus n plus 1 and n. N is the previous step, and current step, n plus 1 is next step. So we can define the natural number, current number, adding one more. That is the next natural number. So that's why f of n plus 1 is equal to f of n plus 1. So next one is multiples of 2. So current step is g of n. In this case, this is multiplication, so that's why we need to start from 1. So first element is 1, and next element using this definition, g of n multiply 2. So next will be 2, and then 4, 8, 16, like that. So we have seen the factorial. Factorial is like this. The current step factorial multiply with next step number, that is next step factorial. And this is another sequence. It is kind of harmonic sequence. H of 0 is 1. H of n plus 1 will be 2 to the h of n. So the this is will be like this. The current, the first one is 1, second one is 2, 1, that's 2, 2, 2 will be 4, and 2 fourths, 16, and 2, 16. So it shows this kind of exponential sequence. So there is another definition, the recursive definition. So if we suppose that h is mapping natural number to rational number, then we use familiar summation notation. The first one is summation of 0, that is h of 0, and the next step, n plus 1, will be summation of h of n plus 1, and the previous step summation from 0 to n, 0 to n plus next step. So there is also product notation. At the beginning, h of 0 is equal to I 0 to the 2. I missed this initial setting here. Okay, so yeah, this is correct. And this will be multiplication instead of that. So anyway, we can define summation and product using that. And we know, we have seen this last class, Fibonacci number is defined by recursion. So there is two recursive core here and here, The one is one step before and two step before. If you combine them together, you can get a current step. So when you want F2, that is F0 plus F1. So 1 plus 0 will be 1, and F3 will be 1 plus 1 is 2. Here is that, and we can use strong induction to prove this. And so in this case, I want to show the two bounding of this Fibonacci, upper bound and lower bound. The first time we're going to see upper bound. So we can assume the upper bound of Fibonacci will be 2 to the nth. And first time we're going to give this upper bound, the Fn is less than 2 to the nth. So we want to prove that. The base case will be start from 0. F0 will be 0 and 2 to the zeros, that will be 1. So anyway, that is greater than 0. It is true. Next step, we want to assume the previous step, P of J will be true. Then we want to prove P of K plus 1. So in this case, that is Fk plus 1 is less than 2 to the K plus 1. Okay, K plus 1. So what we need to prove, we need two K's. So when K plus 1 is equal to 1, and when K plus 1 is greater than equal to 2. The first one, F1 is 1, and that is less than 2. It is simple, that is true. If K plus 1 is greater than equal to 2, Fk plus 1 is Fk plus Fk minus 1 by definition. So that means that is 2, we know this Fibonacci side, we may apply the bound, upper bound, and upper bound will be 2 to the k's plus 2 to the k minus 1 by definition. So anyway, that is less than 2 to the k's. That is, we can simplify them. That is 2 to the k plus 1. That is the same to this. So we know this. These two are same, and these two are same, and the inequality is true. So P of k plus 1 true in this case. We found the upper bound of Fibonacci by the strong induction. Okay, let's look at the lower bound. So maybe Fn is greater than or equal to 2 to the n divided by 2 minus 1. So when you have or n that is greater than or equal to 2. So we'll set the claim F1 is less than 2 to the n half minus 1, and base case will be F2 equal to F1 plus F0, that equal to 1, and we have right side, 2 is here, this will be 1, and minus 1 will be 0, that is 1. So they are same. So anyway, the base case is true. Okay, let's try the inductive hypothesis. Just like this, we want to show P of k plus 1. Yeah, we have seen this before. I didn't change this. This will be n minus 2 divided by 2 minus 1. And okay, so now anyway, we don't need to use the definition here. So now we just want to apply induction hypothesis to get P of k and P of k plus 1. But anyway, we can get P of k since k is greater than or equal to 2. But k minus 1 may be only be 1. So we can conclude P of k minus 1. So want to separate k minus 1 is 1 or k plus 1 is 3. Okay, so we want to prove when P of the k is 3 and k is greater than or equal to k is 2 and k is greater than or equal to 3. So when the k is 2, fk plus 1 is f3, that is f2 plus f1, and this is 1 and 1, and there will be 2. Right hand side will be like this. From here to there. So, and anyway, this is smaller than 2 because this is equal to 2 square root of 2. And when k is greater than 3, we can use the definition. Fk plus 1 is fk plus fk minus 1. In this case, fk minus 1 is fine. In this case, we can use 2. So, by the definition, right hand side will be like this. And if we use the definition of the Fibonacci, that will be this, and we can compare them with 2 to the k minus 1 half minus 1. If we combine them together, that will be 2 multiply 2k minus 1 2 minus 1. This will be 1 here, and we can simplify this part like this, and this one was same to this. So that's why we can prove P of k plus 1 is true in both cases. So that's why the low bound also true for the all natural number n is greater than or equal to 2.